With the growing demand for electronic products, more and more circuit systems have been requested for low power, small area, and low cost. With the emergence of IoT device, the requirement for constant voltage for many power management circuits like LDO, buck converter, boost converter, and other circuits are getting even higher. With these trends in technology, reference has become very vital. The voltage reference is used to provide biasing voltage and at the same time compensate for variation of output caused by the change of voltage, process, and temperature. Thus, on behalf of my co-author, Christopher F. Galvez, I ran Cristine O. Calimpusan would like to present our paper titled Design of Low Power Bandgap Voltage Reference with High Power Supply Rejection Ratio for LDO application. In some applications like electronic circuit system in the oil, gas industry, automotive, artificial intelligence, robotics, a voltage reference is needed to provide a stable biasing voltage under extremely high temperature in the harsh environment. So we have here a low dropout regulator, a voltage regulator that regulates the output voltage even when the supply voltage is very close to the output voltage. And under that low dropout regulator is a voltage reference. A voltage reference is used to provide biasing voltage and at the same time compensate for variation of output caused by the change of voltage, process, and temperature as stated earlier. Having said also, Bandgap reference is one of the essential units in analog circuit system. It offers the basic voltage reference to other circuit units, especially in power management supply. And here we have used CMOS Bandgap reference circuit because it is preferred due to its smaller and consume less power. The CMOS Bandgap voltage reference has been modified by many researchers to operate not only under an output of less than 1 volt, but also in low power and with enhanced PSR, and they have been very successful in doing it. The problem is that although the modified CMOS Bandgap voltage reference can operate under an output of less than 1 volt, and it has low power consumption, like 419.5 microwatts, the PSR are higher than 83 dB at 50 kHz has not yet been achieved. With Francisco et al., it has 82.7 dB at 100 Hz only. Paper, we aim to have higher than 83 dB at 50 kHz, 84 dB at 50 kHz specifically. With this gap, there is a need to explore more enhanced PSR circuitry of bandgap voltage reference. And the solution is to design a low power bandgap voltage reference with high PSR or make an enhancement stage for PSRR. Also, many researchers exploited the enhanced PSR, yet the power consumption is high. So this is the second that the researcher needs to address. The challenge for the researcher is to design a bandgap voltage reference that has first a lower power consumption, second low temperature coefficient, third higher power supply rejection ratio, and thus providing an output that has a decent accuracy and can be applied in practical applications such as in portable devices, implantable medical devices, and wireless sensor networks, even an IoT device and other applications. With the mentioned gaps and limitation of the previous literature, this paper aims to design a low power bandgap CMOS bandgap voltage reference. Second, to design a CMOS bandgap voltage reference with a high power supply rejection ratio of 84 dB at 50 kHz. And lastly, to design a CMOS bandgap voltage reference with a low temperature coefficient. Following figure shows the flow chart of the study conducted. This chart contains the process of the researcher used to achieve the objective of the study. The first part of the process dealt more on researching ideas and concepts regarding CMOS bandgap voltage reference in 180 nanometer CMOS process. The second part involves the actual design of low power bandgap voltage reference. In order to successfully design the bandgap voltage reference, the ideas and concepts in the first part must be applied in the designing process. Furthermore, circuit specification must be set before the designing as well as the designing of the startup circuit. This startup circuit is a sub-block of the voltage reference that ensures proper operation of the bandgap voltage reference. And the third part of the The flowchart dealt more on circuit simulation. The circuit is simulated in order to find out if the specifications are met or not. If not, there's a need to fine-tune the design circuit in part 3 until the specifications are met. When the specifications are met, the evaluation of overall performance of the design Bandgap voltage reference circuit was done. Table 2 here shows the system specification of our design. The design used 180 nanometer CMOS process, and the supply voltage is 1.8 plus minus 10%, and the output voltage is 350 millivolts to be applied in portable application, medical devices, wireless sensor node applications. And the quiescent current is 80 microampere for power scarce environment, and the temperature coefficient tells how dependent the voltage reference to temperature variation is set to be 6 parts per million per degree Celsius, ranging from -40 to 125 degrees Celsius. And we have 100 PSRR of 84 dB at 50 kilohertz. The bigger its value, the better noise rejection. And we have the power dissipation, which is set to be less than 150 microwatts. These specifications are based on standard values and depend on the application of voltage reference circuit. After the specifications have been set, the actual design will be followed. The architecture of the design of voltage reference is illustrated here in this figure. The self-biased current source will supply the required voltage for the two-stage op-amp. A startup circuit has also been added to ensure the whole circuit will operate at the desired state. Power gating technology also added as an additional feature to reduce power consumption. The proposed Bandgap core as shown in this circuit consists of BJT transistors Q1 and Q2 and M1, M2. Resistors R3, R2, R1. This BJT here were parasitic vertical PNP type BJT. The emitter size of this Q2 was 8 times that of Q1, and R2 was the same as R3, and M1, M2 has the same value and form a current mirror. The high gain op-amp here in this two-stage, this is coming from this two-stage amplifier, forces the nodes A and B to have the same potentials. Since transistors or BJT Q1 and Q2 have unequal sizes but equal emitter current, we're biased at different current densities. So a p-TAT loop was formed in Q1, Q2, and R1. Also here in our Bandgap voltage reference, we also have the bias circuit, which will bias the two-stage op-amp. A startup will bring out the reference circuit from dead or zero current operating point to its normal operating point. Two-stage op-amp, it generates a higher gain in which forces the nodes A and B for the Bandgap core to have the same potential. For the PSR, this kind of enhanced PSR is used or implemented not only because of its simplicity but also because it consumes little silicon space and has lower power consumption and is suitable for low voltage operation. A power gating is also added as an additional feature. It was a technique used in an integrated circuit to reduce power consumption by shutting off the current to block all the circuits that were not in use, or where the part system was required to be temporarily disconnected from the power source to reduce the overall system power consumption. The Bandgap voltage reference. So for the results and data gathered, we have here first the transient simulation. It is carried out to check the transient response of the voltage reference circuit. This is a crucial step to ensure that the design can start up and power down properly right after a supply is changed. So in here, as you can see, we have a span of transient response from 0 to 1 milliseconds. And at 100 microseconds, the circuit is able to stabilize at 350 millivolts after supply voltage is ramped. Also, we have conducted a temperature sweep from -40 to 125 degrees for the voltage reference. We have known that the smaller value of the temperature coefficient, the less sensitive the voltage reference output to temperature variation. So the curvature here of the band gap is due to the curved nature characteristic of the p-n junction and the compensation of the positive temperature coefficient. For TT corner, we have got 6.93 parts per million per degree Celsius. So in order to simulate the behavior in the real world, we have conducted a three-corner test. These tests are the parameters that slightly alters the characteristic of the models used in the real world. So we have got for TT, we have 6.93 parts per million per degree Celsius. SS corner 21.06 parts per million per degree Celsius. FF 10.25 parts per million per degree Celsius. Now these temperature sweep are tested in the range of -40 degrees Celsius to 125 degrees Celsius. As you can see, there is a slight variation despite the fact of the variation of the temperature. And to test the voltage sensitivity of our voltage reference, we have sweep our voltage range or the input voltage from 1.6 volts to 2 volts, and we have get the different values from the different corners TT, SS, and FF. We have get 0.46%, 0.67, 0.73% for TT, FF, SS corners respectively. PSRR also obtained based on the typical condition with supply voltage of 1.8 volts and a temperature of 27 degrees. For frequencies at 50 kHz, the circuit achieves a PSRR at least of 84.3 dB, which achieved the goal of the least 84 dB at 50 kHz. We also have used a Monte Carlo simulation to model the probability of different outcomes in the process that cannot easily be predicted due to the intervention of random variables. And we have conducted the Monte Carlo from 1.6 volts to 2 volts input voltage with 100 iteration, and we get 100% yield or 1, the mean of 350 millivolts, and standard deviation of 16.2 micro. And we also conducted the Monte Carlo analysis for the temperature sweep from -40 degrees Celsius to 125 degrees Celsius with 100 iteration. We have get the yield of 1, mean of 350 millivolts, and standard deviation of 135 micro. We also measured the power dissipation of the voltage reference. For the normal operation, we get 84.48 microwatts, and for the power dissipation when power gating was enabled, we get 1.6 nanowatts. In here, we have the summary table of the Bandgap reference. The actual design output are here. So a low power, low temperature coefficient with high bandgap voltage reference is presented in this paper. The researcher designed the circuit in 180 nanometer CMOS process. The result shows the voltage reference can operate a minimum of from 1.62 to 1.98 volts or plus minus 10% of 1.8 volts, and obtain an output of 350 millivolts that is independent to voltage and temperature variation. The quiescent current is 46.99 microampere at room temperature at typical corner. The temperature coefficient result was 0.693 parts per million per degree Celsius at -40 degrees Celsius to 125 degrees Celsius of temperature span, and has yielded 100% using Monte Carlo analysis with 100 iteration. The circuit has obtained a higher value PSRR with 87 dB at 100 Hz and 84 dB at 50 kHz respectively, with a total power dissipation of 84.48 microwatts. So in conclusion, the design has obtained a low power consumption of 84.48 microwatts in normal operation. The design has successfully obtained the target PSRR 84.3 dB at 50 kHz. The design has low temperature coefficient of 6.93 parts per million per degree Celsius in TT corner. Overall, we have obtained our target objectives. So that would be all. Thank you for all listening.